Good morning, students. Welcome to Thursday, April 16th, 2020. Let's do some physics. Today, our main topic is going to be looking at conservation of energy. So, learning targets. I can explain what it means for energy to be conserved. Okay, this is you. You can explain what it means for energy to be conserved. And then we can use that concept of conservation of energy as a basis for performing calculations. And what we're going to find out is, in some cases, we can do calculations that we already, like some of the acceleration calculations we did a couple chapters ago. This will give us a new way of looking at them. And in some ways, sometimes it's easier. And it just gives us a better overall understanding of how this world fits together. So, we're talking about conservation of energy, and for our class particularly, we're talking about conservation of mechanical energy. And in science, that word conserved means it cannot be created, it cannot be destroyed. Okay? So we say energy cannot be created or destroyed. All that can happen is it can change from one form to another. The total amount stays the same. And you might be thinking, well, wait a minute, we talk about trying to conserve energy, and what we're usually saying is we want to use less energy. If the energy can never be destroyed, what do we mean by that? There's all sorts of different forms of energy. Okay? And honestly, I just realized that I forgot at home a prop that I was going to use with you guys. I had 3 light bulbs. The first was a regular old-fashioned incandescent light bulb, and it's labeled as 60 watts. The second was one of those compact fluorescent bulbs. I don't know how to draw that. It's labeled at 13 watts. And the third looks a lot like the first one, but it's an LED, and it's labeled 9 watts. Let me tell you what a watt is. A watt means it uses a joule per second. So that light bulb, when it's on, is using 60 joules of energy every second. And you're saying, well, wait a minute, Mr. Up, you just said that energy can't disappear. What do you mean by using it? Well, we're taking electrical energy, 60 watts of electrical energy, and we're trying to turn it into whatever energy. What do we want from a light bulb? I would say that we want light energy. We're using, to get the light out of that bulb, we're using 60 joules of energy every second. Now, the reason I wanted to show these 3 is this bulb gives off essentially the same amount of light as that one, but it's only using 13 joules per second. And this one gives off the same amount of light. Actually, I think it gives off a little bit more light, and it's only 9 watts, 9 joules per second. So here's the problem. The purpose of these all is to produce light. But if you've ever been around one of these old incandescent bulbs, if it's been on for a few minutes, they're incredibly hot. If you try to touch that bulb, it will burn you. Well, what good is the heat? Imagine in the hottest days of summer, and you got some light bulbs on, the last thing you want is more heat in your house. But these bulbs are putting off a whole bunch of heat. In fact, I think the number is that about 70% of the energy, of the electrical energy that's going through this bulb, is turning into heat energy, and only about 30% of it's turning into light energy. Don't quote me on those numbers, I'm pulling those from memory. Now, if you go to the compact fluorescent, I believe the numbers there are more like you flip those over, 70% of the energy that's used turns into light, and only about 30% goes into heat. And with the LED, it's getting closer to 90% of the energy going into light and only 10% of the energy going into heat. So energy can change from one form to another. Can't be created or destroyed, but some forms of energy are more useful to us than others. Okay? So a lot of times that heat energy or noise or things like that, which are forms of energy, aren't useful to us anymore. Okay? So if I have a gallon of gasoline and I can think about all the chemical potential energy stored in that gasoline, I put it in my car, and a very large portion of the energy from that gasoline turns into heat and noise, and only a relatively small portion of that energy actually moves me from point A to point B. The total amount of energy has to add up, but not all of it stays useful. Okay, now let's back up to just our physics problems here. And we can do certain types of problems involving just the mechanical energy, talking about the kinetic and the gravitational potential and the elastic potential of certain systems. And if we can ignore friction, that mechanical energy is often conserved. Now, friction's always present, but there's lots of situations where the friction is very small and very minimal. And so we do idealized cases. You know, as starting physics students, we do a lot of that, where we take the ideal case and let's ignore friction on the problem. So what we're going to do is we're going to imagine changing these forms of energy from one to another. Sticking with the ones that we just were talking about yesterday. We're going to have, like, for example, we could change potential energy, gravitational potential energy, into kinetic energy. I could drop an object, and it starts out with gravitational potential energy, and as it's falling, its gravitational potential energy is getting less because its height is going down. But as it's falling, it's moving faster and faster, so its gravitational potential is changing into kinetic. And right at the instant it hits the floor, it's going to have its maximum kinetic energy and its minimum gravitational potential energy. At the top point, before it starts moving, it's got its minimum kinetic and its maximum gravitational. Okay? I could change elastic potential into gravitational potential. I could change elastic potential into kinetic. I could change kinetic into elastic potential. Whichever way it is, I can change one form to another. Just a reminder, here were our equations. So kinetic energy, 1/2 mv squared. Gravitational potential energy is mgh. And elastic potential energy is 1/2 k delta d squared. So we're going to need these. Hopefully you have them close by as we go through. We're going to work a few sample problems down. Be sure that you're working them with me. All right, Mr. Rupp, mass 136 kilograms, steps off a 10.0 meter diving platform. How fast is he moving when he hits the water? Don't know why I have an extra capital letter there, sorry. So I'm going to draw a little picture. So here's Mr. Rupp. And he's going to step off. And we know this distance, 10.0 meters. We know my mass is 136 kilograms. Do we have anything else? Now, if you think back, you hopefully recognize that we could go back to our old arsenal and we could solve this problem using our acceleration equations. I don't want you to do that right now. Our goal here today is to try to work on using conservation of energy, a different thought process. So, here's where our physics skills come in. We got to recognize the different types of energy. So when I look at this, I say, hey, I'm above the water, so I'm starting out with some gravitational potential energy. And as I fall, I'm going to be moving faster and faster and faster. And so down here is going to be my maximum kinetic energy. That's how I'm going to do this problem. I'm going to say gravitational potential energy. What happens if all of my gravitational potential energy turns into kinetic energy? Okay? So, next step. We write in what those two were equal to, how they were equal to each other, or what, I'm sorry, the formulas for each of those energy expressions. Gravitational potential energy is described by mgh. Kinetic energy is 1/2 mv squared. Look at that. There's mass on both sides. So I can cross those right out. It doesn't matter if I'm dropping off this platform or if you guys are dropping off the platform. So I'm undoubtedly the largest person in our classroom if you were all here. Take the smallest person in our classroom, and it doesn't matter. Mass doesn't matter in this problem. Now, what was I looking for? I was looking for how fast. Right there's a velocity. So let's solve for that. I got to get rid of this 2, so I'm going to multiply both sides by 2. So 2gh equals v squared. So v equals the square root of 2gh. And if that looks familiar to you, it should. Because if we had done our old acceleration problems, and we take our third equation from that arsenal and work it out, we'd get that same thing. We probably would have had a listed here, but we know that the acceleration involved is g. A is g. Okay? All right, so I'm going to plug in some numbers. V equals square root of 2 times 9.80 meters per second squared times, my height was a 10-meter platform. Okay, looking at labels, this is going to be meters squared per second squared. If I take that out of the radical, I've got meters per second. Square root of 2 times 9.8 times 10, close my parenthesis, equals 14. So I'll write 14.0. meters, I'm going to hit the water going 14.0 meters per second. And Carson's going to hit the water at 14.0 meters per second, and Ethan's going to hit the water, and Caden and Bailey and Mary, we're all going to hit the water at 14.0 meters per second. All right. We solved it by way of a conservation of energy problem. And really, it's a very simple way of thinking about the problem. In some ways, I think easier than what we did back with our acceleration formulas. All right. Example 13. Mr. Rupp has a recurve bow. All right. It's got a spring constant of 365 newtons per meter. If he pulls the arrow back 40 centimeters, how fast will the arrow be moving when it leaves the bow? Okay, so let's think about our energy forms. My question is, how fast? If I'm dealing with a speed, I'm thinking about kinetic energy. Now, I've got a bow that I'm stretching the string back on. I'm drawing the string back. So that's going to be elastic potential energy. So I'm going to start out with elastic potential energy, and I want to change it to kinetic energy. So I'm going to imagine that all the potential that I had stored in that bow turns into the kinetic energy of my arrow. I think I forgot to give you a piece of information that you need here. We're going to set these equal. Let's look at the math. This is 1/2 K delta D squared, and this is 1/2 mv squared. The 1/2s are going to cross off. I told you the spring constant of the bow, and I told you the draw, how far it was pulled back. It's not actually the draw length, but it's the distance the arrow is pulled back. We need to know the mass of the arrow. And I forgot to look that up. I am not a hunter, so I'm just going to kind of think 85 grams. Okay, 85.0 grams. So, again, I want to know how fast, so I got to solve for V. So the first thing I want to do, divide both sides by M. So, divide by M, divide by M, I can cross it off over here. So V squared equals K delta D squared over M. V equals the square root of K delta D squared over M. Okay? V equals square root of spring constant, 365 newtons per meter. All right, the arrow is pulled back 40 centimeters. I got meters and centimeters. I don't want those mixed together in the same problem. So I'm just going to change that. That's going to be 0.400 meters. And that's squared, so I'm going to do that again, 0.400 meters. Okay, and I got to divide by my mass. There too, I don't want grams in there because I know a kilogram is part of my Newton. If I got kilograms in there, I don't want to mix kilograms and grams. So I'm just going to move my decimal point 3 places. So this is 0.0850 kilograms. And those of you who are bow hunters, if I'm way off on my mass of arrow, I apologize. Just guessing a little bit. Okay, ready to do the math? So we've got a square root of 365 times 0.4 times 0.4 divided by 0.0850 close parentheses equals 26.2. I should go through and try to double check my labels. Meters, cross off. A Newton is a kilogram times a meter per second squared. So the kilograms are going to cross off. And I'm going to have meters squared per second squared, comes out of the radical, meters per second. Okay, I'm going to write that out. The Newton was a kilogram times meter per second squared. We had a meter on the bottom. We had a meter on the top. We had another meter on the top. And we had kilogram on the bottom. Okay? So when I get rid of a bunch of stuff, kilogram is gone, meter is gone. I've got meter squared over second squared. Take it out of the radical, meters per second. All right. So I think that's kind of a reasonable. That's not a real fast speed coming out of a bow. So somewhere along the way, I made some poor estimates, or maybe it's just a really low-powered bow. All right, one now I'm taking that a different bow, slightly stronger spring constant, same length, and I'm going to shoot the arrow straight up. So let's go with, again, the mass of the arrow, 0.0850 kilograms, 85 grams. So how do we analyze this one? Again, I've got this bow. I'm pulling back the string, so I've got elastic potential energy. But now I'm saying, how high? Well, the height above the ground is associated with gravitational potential energy. So I'm going to imagine all of my elastic potential turning into gravitational potential. And everything else, now we plug in our formulas. 1/2 K delta G squared mgh. I'm looking for how high, so I'm going to divide both sides by mg, divide by mg, so h equals, all right, K, well, let's draw this all out. 1/2, the 2's on the bottom. The K is 385 newtons per meter. The distance, this is the distance that the spring is stretched, that was, I'm going to change that to meters, 0.400 meters, and that's squared, so I'm going to do another 0.400 meters, and I'm dividing by the mass, 0.0850 kilograms, and I'm dividing by G, which is 9.80 meters per second squared, so those flip back to the top. Okay. A Newton is a kilogram times a meter per second squared. I've got kilogram and meter per second squared on the bottom. So I can take off that Newton with this. And then I had meters here and meters here. I'm left with meters. And I'm looking for a height. So, you know, when you get to the end and your labels equal what you're looking for, you got to feel pretty confident in the problem. So I'm going to go through and take let's see, I'm going to start with my 385, and I'm going to divide by my 2 so I don't forget that. Divide by 2, I'm going to multiply by 0.4, I'm going to divide by 0.085, I'm going to multiply by 0.4 again, I'm going to divide by 9.80, hit enter, and let's see, I think we've got 3 sig figs, so I can go, it's 36.97 meters, so I'm going to have 37.0 meters. All right, so there's 3 examples changing one energy form to another. And it's some of the problems, especially if we weren't involving this spring constant, some of those problems look very much like what we had with acceleration problems earlier this year. And yet, I think it's almost a simpler way of looking at it. It's I'm drawing a blank on words right now, I apologize. It's a different concept. It's an important physics concept. I want you to understand that. I want you to practice doing some problems in terms of conservation of energy. So I'll give you a couple of practice problems to do, And as always, let me know if you have any problems. I keep hoping that people will pop in on one of those Zoom conferences once. If you have difficulties with stuff, join me on one of the Zoom conferences, and I can talk to you. I can hear your question. I can draw things out for you on paper. There's a couple of students who have done that, and it works. I can answer your questions better on there than I can through an email. So, take care of yourselves. Stay safe. See you soon.